Yeah, good. Okay, lots to do today, so let's start. All right, exam one. If you took the exam Wednesday night, your score is posted on Blackboard, your raw score out of 21. Here's what you do to get your score out of 100. You're going to take 3.7 times whatever that score out of 21 was, and add 23. Okay, and that'll give you a score out of 100. When I do that for everybody, here are the results of the class. So there's the distribution, 90s, 80s, 70s, 60s, less than 60. Average 73, median 75. Okay, so this is the easiest test, okay? Because when we start getting into the nitty-gritty of calculus, it's when it gets harder, okay? So if this didn't go as well as you hoped, let that be a motivator, don't let it disappoint you, just let it motivate you to change your approach to the course. More office hours, get started on homework earlier, watch the videos soon, like the night after class, change your approach, and it's going to take more effort outside of class. Okay? Let's go over the 3 most commonly missed items. Yeah, talk over that. So, if you want to find out more details about your performance on the exam, you can go to anybody's office hours. If you go to the TA's office hours, they will have your detailed results and blank exams to look at. If you want to look at the exam you wrote on, as to go over it, then you need to come to my office hours. I have those exams, okay? So, but any of the TAs, you can go and look at a blank exam and know every answer you put on all the items. So you'll find out which ones you got right, which ones you got wrong. You can spend as much time going over it individually, okay? But if you want the exam that you wrote on, you need to come to my office hours. Okay? Grades. I've told you this before, but I'll have to keep reminding you. On Blackboard, if there's some total or overall grade, it's trying to calculate a total or overall grade, ignore that. I just use Blackboard to record individual grades. All those points have different weights, so if they're trying to calculate a total, just ignore any total or overall, okay? I will, a couple times through the semester, calculate a current grade for you, okay? We're going to make a new homework and quiz schedule I think you'll appreciate. So instead of having homework due every day, we'll just have homework due Wednesdays and Fridays. So that way you don't have this Monday homework that you can't get help and support on, okay? And then we'll do our 10-minute quizzes on Mondays, which cover the previous week's material. So the Wednesday homework, the Friday homework, and then the quiz will be, for the most part, on that stuff. And then we won't turn in a written homework on Mondays, okay? So we will have a quiz this Monday. We'll have a 10-minute quiz at the beginning of class Monday, but your next written homework will be due Wednesday, okay? Any questions about any of this kind of stuff? Again, if it didn't go as well as you planned, let it motivate you to put more effort in. Yeah.
If we have a question about our grade before, like those...
Yeah, in office hours, yeah, to me. So in office hours, if you are interested in your grade, come to my office hours and we can get a rough estimate. No, in this thing here?
Yeah.
No, so then if you did the honor statement correctly, you read it carefully and there'll be an additional point for that. Okay. Don't throw rocks off the top of buildings. Okay. Here we go. Okay, here we go. We got half an hour to cover quite a bit of stuff. So let's really focus in. Don't try to avoid the temptation to talk when I haven't given you that kind of permission, okay? So here we go. We got 2 painters. and they have started painting their respective houses. At a certain point, the first painter, we'll call him P1, has already painted 250 square feet. Second painter, P2, has already painted 400 square feet. So, how am I making sense of this situation here, visually? What does the bottom bar represent? What does the bottom bar represent? It's not a person. So it's not painter 1. So total square feet painted by P1. And we're going to call that X. That variable X will take on the values of the total amount painted by painter 1. Therefore, the blue, the upper bar is total amount, total square feet painted by P2. Don't have page 1 of my notes. Okay, I have to wing it. Here we go. So we're gonna let painter 1. He's gonna paint. Oh, so and then each vertical bar there is 100 square feet. Okay, so our reference here is the vertical bar is 100 square feet. So how about it? Painter 1 paints an additional 200. So I'm showing the bars thinner. So the thinner part of the bar represents what? Change. And we represent that how? Delta, right? Does the total amount painted by painter 2 maintain a relative size to the total amount painted by painter 1? Yes or no? I'm hearing yeses, I'm hearing no's. We want convincing mathematical proof. Either yes or no. Does the total amount painted by painter 2 maintain a relative size with the total amount painted by painter 1? All right, so we want to investigate this numerically. How can we investigate this numerically? How much did total painter 1? He started with 250, is that right? And 400? And how much more did painter X, or yeah, painter 1 paint? 200, so how much total has he painted now? And how much more did painter in that, while painter 1 painted 200 more, how much did painter 2 paint? 250 more, total of? So convince yourself numerically whether or not you can make a conclusion as to is the total amount painted by painter 2 maintain a relative size to the total amount painted by painter 1. Numerical proof. Okay, here's what I suggest to kind of make sense of this and organize. Make a table of values. Make a table of values. So when X is 250, Y is, and when X is 450, Y is 650. How do we check to see if relative size of these total amounts painted is maintained? Stays the same. How do we check? Okay, I heard subtraction and division. Which one? Not both. Relative size is division, right? Quotient. Quotient. So what is our, so we're going to look at y over x. Did anybody calculate these? This is what?
1.8.
Thank you, 1.8. And this is?
1.4.
4 something?
Yeah.
Is relative size maintained? No. How about relative size of the changes? Really, that's what we've been talking about with constant rate of change, right? It still might be constant rate of change, right? If the relative size of the actual quantities is not maintained, that doesn't put us out of the running for constant rate of change, because constant rate of change is about the relative size of changes. So what about relative size of changes? Yes, sir. Is that wrong? I'm just listening to you guys, so thank you. Are we more accurate now? Same conclusion? Same conclusion, okay? What about change in x and change in y? Relative size maintained? Saying no. Yeah?
Do we need more change to figure it out? We need one more cycle.
He says we need more information. He's right. All right, now painter X. Painter 1, sorry. Painter 1's going to paint. What did he do? 200. Now he's going to paint 300 more than that. Maybe. Is that 300 more? Okay. Do the math. So, is the relative size of the change by a painter, amount painted by painter 2, maintained relative to the change in the amount painted by painter 1? Everybody do it. So no just watching the screen. Get involved. What's the total amount painted by painter 2 now?
1025.
1025. So if we're checking for relative size, we're checking, what kind of values are we checking? Quotient of delta y to delta x. So we need some ordered pairs of delta y and delta x. So someone give me some one that we know. What's a delta x and corresponding delta y that we know? 200 and? Perfect. Is there another one we know now?
300.
Anybody do something different? Good. No one?
250 is that?
Yeah, go ahead.
You can do the total change.
Yeah. Yeah, so this is a valid change from 250 to 750 is 500. Corresponding change in Y? 625. Okay, so then we check delta Y, delta X. What is it here? Conclusion.
Yes.
So what is varying with constant rate of change? Is delta Y varying with constant rate of change with respect to delta X? Or is Y varying with constant rate of change with respect to X? Talk to the person next to you. What's varying with constant rate of change? Delta Y with respect to delta X? Or Y with respect to X? Go. Okay. How many people think that Y is changing at a constant rate with respect to X? One person. Anybody else? 2, 3. Don't be shy. Because you're right if you raise your hand. Y is changing at a constant rate with respect to X. What's the test for that? The test for constant rate of change between two quantities is if their changes maintain a constant ratio. So it's about Y and X. It's about Y and X changing at a constant rate with respect to each other. Okay? So we're doing all this with the changes, but it's about those original quantities, whether or not they... I asked the right question, didn't I? Okay. All right. Yes, it's about Y and X. What's that?
Like, was it the idea that if you saw, I don't know, if you show,
What? I don't know.
like, how do you know that?
Because two quantities change at a constant rate of change if the relative size of their changes is maintained. The relative size stays constant. And that's what we have. We have that their changes, the change in Y is always 1.25 relative to the change in X. It's always, however much X changes, Y changes 25% more than X changed. That's one way to say it. Okay? Cool. All right, so interpretations of this number. So we know that's the relative size of the change in Y to change in X. What else do we know about that number? What else can we conclude about that number? So besides the fact that that's the ratio of, or the quotient, delta Y over delta X.
The constant.
Okay, tell me.
It's the constant multiple between the rate of change of X and Y.
Okay, he said the constant multiple between the rate of change of X and Y. So he's kind of, Kenny.
Change in Y times the constant multiple. Wait, the change in Y is the constant multiple times the change in X.
Right, if you knew any change in X, how could you find the change in Y? Multiply by 1.25. That's the meaning of relative size. That delta X is always 1.25 times as great as delta X. So not only is this the ratio, but it's the constant multiple that would give us any change in Y if we knew a change in X. Okay, how can we think of that number related to the quantities X and Y now, rather than always related to delta X and delta Y? So is there a way we can talk about 1.25 in terms of the original total amounts painted X and Y? Anyone? We did it once before, yeah.
Would it be that painter 2 paints 1.25 times as fast as painter 1?
he said painter 2 paints 1.25 times as fast as painter 1. Or the value of y changes 1.25 times as fast as x changes. Is it true?
Wouldn't it be after that point that he's gotten to 460?
Okay, so we know for sure, maybe we don't know about before,
Yeah.
but we know for sure that after this given point.
Yeah.
But which is what he said generally true. So is y changing 1.25 times as fast as x?
Yes.
This is what derivative is about. So those of you who've taken calculus before, this is what derivative is about. How one quantity is changing relative to another. So this ratio of the changes then tells us that y is changing 1.25 times as fast as y is changing 1.25 times as fast as x. I'm going to write it down because this is so crucial. Y changes 1.25 times as fast as x changes. This is what the derivative is about. Okay, cool. So now I want to analyze the same situation on a graph that you're used to, right? The XY graph. So how do I have to adjust my picture so that we can talk about it in what we call the Cartesian plane, the XY plane? Take the we've seen this before, right? Take the change in y, the blue one up top, and do it. Put it on the end of the. I can do it. Let's move it back here. Maybe. Come on, like that. So I just took the blue one and just flipped it up and put it on the end. And then what happens? It's the same way. They'll change together the same way. And the very top of the blue bar is going to trace out all the points that would be on the graph, right? The top as you let x increase, y will increase 1.25 times as much. Change in y, and then this top point will track out all the points. Okay, so I got a different view of that here. So there it is. Okay, so the very top of that blue bar will track out all the possible combinations of total painted by painter 1, along with the total painted by painter 2. So we had some points already, right? So we have 3 XY ordered pairs. Oh, don't worry about that. Okay, so can you see those points? Are they big enough? We had 250, 400, 450, and is it 650? 450 and 650, and then 750 and 1025, right? So let's kind of talk about relative size as it applies to this type of graph, okay? So this type of graph. So right here at the starting point, I'm going to do a change of x of 50. How can I show that? How can I show a change of x of 50? Start here and go where? Right there, right? Is that delta x of 50? How can you find out how much y changes? Go, do it. So everyone should know how to do this by now. How could you find out how much y changes? Go. Okay. That should be coming second nature now. You've got delta x is 50. Delta y then will be, not the answer, but how would we get it? Always 1.25 times the change in x. So we're going to take 1.25 times 50. What is it? 62.5. Okay, I'm going to move this up to the next point so I can finish that. Okay, so when x went up 50, y went up 62.5, and it gives us a new point on the graph. So right there, what is the total? How could you find the total amount that painter 2 has painted? It's just logic if you're following what's going on. We got 250 and 400, and we just got a change in y of how much? 62.5, therefore 462.5. So x is increased by 50, so we got 300. Y increased by 62.5. So we took the old, listen, this is crucial. We took the old y, we added the change in y to get the new y. Common sense, right? Okay, I want you to do that same procedure. So first, we're going to go to our second point, which was, what was our second point? 450 and 650. So now I want you to do a change in y, a change in x of 150. So painter 1 is going to paint 150 more. I want you to find how much painter 2 additionally paints, and then the total that painter 2 has painted. Go. Same approach here. Okay, let's get a volunteer. Let's see here. How about blue shirt right there? Blue shirt. Yep, that's you. So how much did y change, or how would you find how much y changed?
You multiply times 1.25.
Multiply what?
Change in x.
Okay, so 1.25 times,
Change in x.
which was?
150.
Okay, and then how am I going to find now the new total that, and so what's the new amount that x is painted? Or painter 1? 600, because it's 450 plus his change.
600.
And how would we just, how would we find how much painter y now has, in total has painted? How much? Okay, so tell me the numbers. 650 plus the change in y, right? So this will be 650 plus my delta y. And what was delta y? So let's see if I can do that in my head. 837.5? 837.5 is the new y. Okay, let's see. One more time. Change of x of 250. Go. Change of x of 250. So from this point, which was 750, 1025. Here's the current point. 750, 1025. Change of 250. Change of x. Okay. Want to do it? Okay. Let's listen. Here we go.
So, delta y will be 1.25 times 250, which is 312.5.
Okay, let me. You agree with that, everybody? Okay, they like it?
Add that to the original y, and that'll be
Which was what?
1025.
New y equals the old y plus the change in y. New y equals common sense. What do you get?
All right, it's 1,337.5.
These guys are painting fools. All right, so go ahead and do it. Get in the right place. Oh. Don't move. Okay, so when relative size is maintained, so we're starting to develop a locus of points. When relative size is maintained, that change in y, in this case, is always 1.25 times the change in x. How does the locus of points then emerge? How does it emerge? Yeah. So if you get, it's kind of like similar triangles, right? These are like, that relative size is maintained, it's like you've got similar triangles, and so the points it would be worth oohing if I could do it. Right, so the points emerge as a straight line when the relative size of the changes is maintained. It's like that change in y relative to change of x stays the same. So you get this locus of points that emerge in a straight path. Okay, what's the formula for slope? What's the, back 8th grade, 7th grade? No, the formula for slope. If you had 2 points, okay, I don't want to have to keep you late. But what is y2 minus y1? Is that familiar? The ratio of the change in y to change in x. What is that number? What number is that? And that's the constant rate of change, right? Is that the steepness of the line? Is that the steepness of the line? What is our constant rate of change here? Is that the steepness of this line, 1.25? What's the steepness of 1? What's the steepness of 1? 1 over 1, right? Every time you go a distance in x, you go the same distance in y. So in steepness, how would you describe that? $45-degree angle? Yeah, 45 in steepness. Talk about steepness. The steepness of 1 is like that line I just drew, like red. Like just going halfway between horizontal and vertical, right? Halfway between horizontal and vertical. That's a steepness of 1. So a steepness of 1.25 is even a little bit steeper than that. Why can't we say slope is steepness or inclination? We're looking at it right here. What is our slope? Our slope is 1.25, but that line I just showed, that's a steepness of 1.25. So this word slope is deceiving, right? Because you're thinking, oh, like the roof or like the ski slope, right? It's like how sloped is it? How steep is it? But mathematically, you can't have that conception of slope. You cannot have a visual conception of slope. It can only mean the value of the rate of change. So if slope to you is some kind of visual thing of the graph, you need to erase that. If you're talking about slope, it can only mean constant rate of change. Okay, and so, and why isn't the steepness of this line 1.25? Yeah.
Isn't it because if it were to be polar, where it's derived from like a circle where it's steepness relative to?
No, you're off on the wrong track.
Because it's the scale of your axis is weird.
Right, because we can change the scale. And when we change the scale, the steepness of a line will change. Steepness will change. But does the slope change? No, the slope is the same. The slope is that value of constant rate of change, okay? So slope, take away any visual connection you have with slope, and its meaning for you should only be that value of the constant rate of change, this thing we've been hammering, the relative size, the change in y to change in x. Because here I'm showing you a steepness of 1.25. It's nothing the same as the way we're showing our painter's relationship. Okay? All right, so one more thing. So we're going to use that same idea to get this equation of this line, okay? So we'll start at this point. What's the value of this, the coordinates of this point? Painter 1 has painted a total of 450. Painter 2, 650. If I want to represent now any point on this line, I can just, pick one here, not at any particular value, and just call it xy. I could have picked that one, I could have picked this one, I could pick any that I want, right? There's an infinite number of points in this line. I just pick any single one and make it have the meaning of any point. So if it's any point, then x and y will change, right? X and y can change. So I want to do the same thing we just did 3 times over. That was so easy, right? What was the first thing we looked at? How much is the change in x from 450 to x comma y, or to x? How much is the change in x? Go ahead. Oh, I thought you were going to say it. So you got it. X minus 450. Isn't that change just for x minus 450? Okay. So now you finish. So using that delta x, you want to find the corresponding delta y and find the new y. Do the same thing we did just 3 times before. Find the corresponding. It's just now you'll have expressions rather than values in the end. Okay. So find the corresponding change in y. Find the new y. Go. Okay, what's the change in y? How about the gray shirt over there on the end, on the aisle? The change in y?
It should be
1.25 times, which is?
I got, I think like 725 on this.
No, this. Just this, because this could be any point. This could be any point I could have chosen. So that's why I'm calling it xy. So you're right, 1.25 times the change in x. Our change in x now is x minus 450. Is it okay? Hopefully that's not too big of a stretch. It's just that x, we could have picked any point, so we're just going to keep it as any point. Is it okay?
That's the change in y, right?
Yeah.
I was meant to do that over here. I put it in the wrong place. That's the change in y. This is here. Sorry. Thank you. I will make mistakes. Please call them out as soon as possible so I don't dig too deep of a hole. Okay? Are we good?
Yeah.
New y equals old y plus change in y. What's the old y? Plus? Don't miss this. All right? We're going to need this. So what did we just represent? No, but what did we just represent with that equation? Every point on the line. We just represented every point on the line. Pick an x. This will give you the corresponding y for that point. So this is what we mean by the equation of the line. It represents every point on the line. And this has meaning because it we see how it emerges, right? We start with delta x, we get delta y, we add it to the old y, and it gives us the new y, right? So you can see what's happening in that equation. We're going to need this, so you're going to learn this. The days of just y equals mx plus b are over, okay? So it is valid. It's valid, but it can't be your only little narrow view of linear function. You have to have this. You have to be good at this. Change in x, corresponding change in y, add to the old y, gives you the new y. And then, therefore, that's every point on the line. Okay. So, any questions? We're going to do top hat, and we're not going to do cards today. Just top hat.